Now that you've got an overview of how our system works, it's time to take a look at some of the logical relationships that we can explore within this system. And the first thing we need to be able to do in order to do that is compute the truth value of a sentence. We can in principle compute the truth value of any sentence within our system. And we do that by using the semantic rules for the operators. So let's start with a simple example. Suppose we have the statement tilde a, or as I would encourage you to read this at this point, not a. Semantic rule for tilde tells us that the statement's value should be the opposite of whatever it's the negation of. In other words, the sentence that it was constructed out of in this construction process that I was suggesting you think of. And so this is the negation of A. A is true, and so tilde A should be false. Now let's look at another example. Suppose we have A dot B, or as I would encourage you to read this, A and B. The rule for the dot is that it's only true when the sentences on both sides of it are true. So the left side is A, which is true. The right side is A, which is also true. So this sentence should be true. Let's look at another example. Suppose we have tilde and then in parentheses A dot B. And this I read as not both A and B. But I don't have room for that in the space I've allocated myself here. The main operator of this sentence is tilde, since it's outside the parentheses. The tilde applies to the complete sentence in the parentheses, so the value of our sentence should be the opposite of that sentence. And we just decided the value of A dot B was true. And so the value of our tilde sentence should be the opposite, false. And you may have noticed there's a kind of a notational convention that I'm following here, where I'm writing the value of the sentence under the main operator for the sentence. And not only that, I'm also writing the value of subcomponent sentences underneath those operators. So the value of A dot B, I've written underneath the dot. We'll come back and look at that in more detail in a minute here. Let's do another example. The sentence tilde A dot B, which says not A and also B. This time the main operator is the dot. And the left side of that dot is tilde A. Just keep in mind that the tilde forms a unit with the shortest complete sentence on its immediate right. So in order to compute the truth value of this dot sentence, we have to know the truth value of the right side, which is B. We already know that's true. And we also have to know the value of the left side, tilde A. Well, we computed the truth value of tilde A earlier, and we said it was false. So the left side of our dot is false and the right side is true. The rule for dot is that both sides have to be true, so that makes this sentence false. Now let's go back and take a closer look at what we're doing here. We can think of any one of our sentences as being broken down into a number of parts, which are subsentences. And we didn't rewrite the value of every single subsentence when we were going through and doing that. But now let's find a systematic way of doing this so that we can do it for any sentence whatsoever. And if we start over, to do this a bit more systematically, we can start by writing the value of the simple sentence underneath the sentence. So with tilde A, let's write the value of simple sentence A, even though I know this might sound a bit pedantic. When we compute the truth value of tilde A, we refer to the value here of A, and we take the opposite. And meanwhile, when we compute the value of A dot B, we can start by writing the values of A and B underneath them. Then we refer to those values when we compute the value of the dot. Since both sides are true, we write down that it's true. In these cases, we had only one operator. In the next two cases, there's more than one operator. And when we have more than one operator, we have to know which one gets done first. And the way this needs to work is essentially that we have to do the main operator last because it depends on the subsentences out of which it is built. So in the third sentence, we need to know the value of A dot B first, while in the second sentence, we need to know the value of tilde A before we can do the dot. But if you have some long, complex sentence, then it can become difficult to sort of reverse engineer the sentence and try to figure out what the main operator is and then do the sub-main operator before that and then do sub-sentences and sub-sentences until you get to the one you have to do first. You could think of it that way, all right. But a simpler way would be to think in terms of an order of operations. So here we have this complex, intimidating looking sentence with all these parentheses and tildes, and we have to figure out what comes first, how to proceed. Let's start by putting the values of the simples underneath the simples. Okay, that takes care of that. But now it looks like we have this really confusing, complex job in front of us. In fact, though, if you look back at the real simple examples we did first, they illustrate an order of operations. And you're familiar with the idea of an order of operations, like in math, you have the order of operations. Please excuse my dear Aunt Sally, right? Or PEMDAS. And that stands for parentheses, exponents, multiplication, division, addition, subtraction. If we have a bunch of mathematical operators without any parentheses to make it clear what comes first, we follow the order of operations PEMDAS, and it's like we have those parentheses. If we wrote everything all the time with parentheses, then there wouldn't be any need for an order of operations other than just, do the things inside parentheses first. And I have good news. The system that we're working with includes almost every sub-sentence goes in parentheses, right? Everything except for the tilde. So we don't need a complex order of operations like PEMDAS. Please excuse my dear Aunt Sally. Take a look at the third and fourth examples above, And recall that we just had to do sub-sentences first. So what that means is that parentheses take priority over tilde, and within any parenthetical group, remember our fourth example includes unwritten parentheses on the very outside. So if we have a tilde and a dot within the same parenthetical group, the tilde comes first, since it's a sub-sentence of the dot statement. So we only need a very simple order of operations. Our order of operations is simply this: parentheses, tilde. So you see, it becomes very easy. All you have to do, you follow the order of operations, parentheses, tilde, just as you followed the more complicated order of operations, PEMDAS, since you were very young. So if we're looking at this long compound expression, let's make a note of the main operator at the very beginning anyway, which is the double arrow. And in computing the truth value for this entire sentence, we just follow the order of operations parentheses tilde, which tells us parentheses first, so we enter into the first set of parentheses, this one, and before we can compute the value of that parenthetical group, we have to do the next smaller set of parentheses, which goes from the left side of the C to the right side of the X, and within that parenthetical group, the first thing that we have to do is the tilde, since tilde takes priority over the dot. Now this tilde is applied to X, so we take the opposite value of X. X is false, so the value of tilde X is true. Now at some point or another, there's going to be a lot of T's and F's flying around here. So here's what I recommend doing. After we use the value of X to get the value of tilde X, that will not be used again. And we don't want it to distract the eye and look at the wrong thing. You don't want to look at this F when you should be looking at this T. So what I advise doing is just kind of cross off the F. Just do it lightly so that you can still go back and check your work, but it's not distracting to the eye. I'm going to use a highlight here, except that we have to remember that the highlight means ignore. Now we continue with our order of operations, parentheses tilde. So we still have to do the parenthetical group from C to X. So C and not X, or C dot tilde X is what comes next. And we're going to write the value of that expression underneath the dot. Now the left side of that dot is this C, and the right side of that dot is tilde X. And we've written down the value of tilde X underneath the tilde. Both sides are true, and so this dot sentence is true. Now I'm going to, again, cross off the values that got us there. So I'm going to cross off the value of C and the value under the tilde. Those don't get used again, and we don't want to look there. In this case, it turns out to be the same as where we do want to look, but just as a general rule, we'll always cross them off. So now we continue following our order of operations, and we work our way to the larger set of parentheses, going all the way from B to the other side of the X. And the left side of this parenthetical expression is B, which is true. The right side is the C dot tilde X thing, which is also true. And the operator we're working with is wedge. So we refer to our semantic rule for wedge, which tells us that it's true as long as at least one side is true. In this case, both sides are true. So the value that we get is true. And again, I'm going to just highlight, or if I was doing this by hand, I would cross off the two values that we used to get this. And we just continue along following our order of operations. We now move outside of those parentheses. And there are, of course, deleted parentheses that surround this entire sentence. So this tilde and this double arrow are in the same parenthetical group together. So what does the order of operations tell us about a tilde and another operator that are together in the same parenthetical group? The tilde comes first, right? The only thing that comes before tilde is parentheses. So we assign the value of this tilde next, and it is the opposite of the expression on its right, which is this whole parenthetical group. The value of its negation is false. And now I'm going to cross off the value of that wedge, because we're not using that anymore. So now we've worked our way through this entire statement, and we have a double arrow sentence. And the left side is A, while meanwhile the right side is this entire tilde sentence. The left side is true, and the right side is false, and our rule for double arrow tells us that it's true if the sides are the same, but false if they're different. So we know that this sentence is false. That's the value of the entire sentence. So now you see that it's fairly easy to compute the truth value of even a fairly long, complicated sentence of this system, just using the order of operations rule, parentheses tilde, and applying the semantic rules for each operator. So the next thing we're going to want to do with this is see how various logical relationships between sentences emerge. And the next couple of videos are going to deal with that.